Okay, so let's continue with reactions of alkenes. We've finished very specific electrophilic addition of alkenes. So now we're going to do some of the other types of reactions on alkenes. So the first one we're going to do is catalytic hydrogenation. So the overall general form of this reaction looks like this. Here's my alkene. I'm going to add in hydrogen gas. But this doesn't actually occur until I add in my catalyst. Now, what kind of catalyst do we use? We often use metal catalysts like palladium, platinum, and use nickel. Okay, so those are some of the typical catalysts that we use. Sometimes you'll see it as palladium on carbon if we wanted to try to get it as small, fine powder as possible. We take carbon, graphite particles, coat it with palladium, and that allows us to create a great surface area. And we add our hydrogens, okay? And just be aware, this is added in syn orientation. They're on the same side, okay? So let's go through this and show you the mechanism for it in some course detail. But we'll talk about why it's syn addition, and then we'll do some examples. So if I have, let's say, my palladium catalyst. This is actually a heterogeneous catalyst because this is a solid and everything else is going to be in solution. I have my solvent with my alkene and I bubble through hydrogen gas and mix it in so that the hydrogen gas is in my solution. So here's my solution. Okay. And what happens is that the hydrogen gas adsorbs to the surface. And when it does this, this hydrogen-hydrogen single bond gets weakened. Okay? It's not broken, it's just weak. Okay? So when that happens, and my alkene comes in, then basically those pi bonds right here, okay, let me just draw this a little bit differently so you can see. Those pi bonds then basically sit right on top of those hydrogens, and so the hydrogens actually add on the same side. They couldn't possibly add on opposite sides because there's not enough time for this to actually rotate around. So when this adds, that pushes these these bonds up. And now my palladium catalyst is ready to absorb more hydrogen gas. Okay, so that's essentially why it actually adds in a syn orientation. So let's do a couple examples. I'm putting palladium on carbon on this one. And when you show, that'll be your final product. Okay? All we did here was add my two hydrogens onto here. What happens if I do something a little differently? Let me give you hydrogen. Let's do platinum. Okay? So when you draw this, you know that your methyl group and your ethyl group have to be cis because the hydrogens add across your double bond on the same side. But remember, the hydrogen can add underneath or it can add on top. So you're also going to get the enantiomer of it. Okay? So just so you're aware that here again, you have to be aware of your stereochemistry in your products. Okay? Likewise, if you do hydrogenation, okay, on this product, well, let's think about it. If I add the hydrogen, let's say from on top, so I have a hydrogen here, pushes that one down, right? That would stay in the same plane, okay? Or let me just do it this way. That goes in the back. This one comes out. My hydrogen comes here. Okay. And then, what about the stereochemistry of this carbon right here because of this methyl? So if I draw it this way, then this methyl has to be in the front. This hydrogen comes here. And then in the back would be a hydrogen. So this is not a chiral center, but just be aware it's these two hydrogens that are added across my alkene. Okay? Since that's not a chiral center, but this is, we also have the enantiomer here. Okay? So that's catalytic hydrogenation. Okay? So let's talk about one other catalyst. Okay? We've only been talking about the heterogeneous catalysts, but there are homogeneous catalysts. Okay, so why would we want the homogeneous catalysts? Okay, so when we talk about the homogeneous catalysts, we can actually get enantio selectivity. So we can choose one enantiomer over another. Okay? Now we can't do it with the solid surface because it can go actually above or below the plane of the alkene. But if we have a homogeneous catalyst, it can actually complex with the alkene before it adds the hydrogen, and that allows us the enantiomer selectivity. So let me just give you an example, just so you know what's available out there, but we probably won't use it. Okay, it's called a Wilkinson's catalyst. Okay, so let me just give you an example of what you can do. So you have this, you have your hydrogen gas, and then the Wilkinson's catalyst actually is a rhodium complex. So let me just go ahead. And this is also should be okay. Okay. And here, because you have these larger groups, that's has no stereochemistry. Hydrogen gas has no stereochemistry, but we can reintroduce our stereochemistry with our homogeneous catalyst. And that's how we can prefer one enantiomer over another. Okay, so Wilkinson's catalyst was one of the first. You might hear something about Grubb's catalyst. Okay, so let's talk a little bit more about reactions of alkenes. Now we do carbenes. Okay, so the two carbenes that we're going to look at is we're going to look at a carbenoid, and we're going to look at one made from basically chloroform or bromoform. But remember, when we look at a carbene, there are two different types. One will allow some spinning here. The other will actually add immediately. Okay, it's a concerted reaction. So we're going to focus on concerted reactions. What that means is this. As my double bond is forming a bond to the carbon, this lone pair is forming a bond back. What you get is a cyclopropane. Okay, so how do we form a carbene? So one way to form a carbene is this. What you do is you use diazomethane. Okay, so your diazo group okay. Right? So we just use a different color arrow here. Okay. What happens is this bond breaks. Use a different color. You form nitrogen gas, which is an excellent leaving group. And now you have your carbene. Okay, so that's one way to form it. It's toxic and explosive. Okay, so using diazomethane is not the best idea in the world, but it is one of the first ways that we use to form, actually, a carbene. So what do we do now? We do what we call the Simmons-Smith reaction. Okay, you have your alkene. You're going to react it with what we call, that's not lowercase h, the carbenoid. Okay, this is called, okay, a carbenoid. Basically, it's acts and behaves exactly like a carbene, but it's not a true carbene because I'm complex to zinc and iodine. Let me just redraw this. Okay, and you get your zinc iodide. All right, so how do you form your carbenoid? You're going to take diiodomethane and you're going to react it with a complex of zinc with copper. Okay, and what you get is your carbenoid. Okay, so this can come in the form of zinc with copper 2 chloride, or copper 1 chloride, excuse me. Okay, so you just need that complex. So what happens is you form your carbenoid. What happens to the copper? Still stays as copper 1 chloride, Cooper's chloride. Okay, so this is how you make your carbenoid. And your carbenoid acts basically as a carbene. Alright, so let's do a reaction with it, and then let's make a different type of carbene. Okay. So we do a reaction with it. Let's try. Okay, so this is basically what you're going to add in there. This forms essentially the zinc complex with my copper. Okay, so this is what you're going to see, but what this forms is going to be your carbenoid. Okay, so from what we saw earlier. And if you do that, then all we're going to do is we're going to form the cyclopropane out of my alkene. Okay, and do I need to draw it with the showing that they're both on the same side? No, because it's automatically known. You can't have a cyclopropane if this is trans and that's these two bonds are trans for each other. So that would be your product. Okay, now we're going to start doing formation of carbenes with alpha elimination. We're going to continue our discussion on alkenes. We were working with carbenes, so we have to talk about the alpha elimination reaction to form carbenes. The way it works is you take something like chloroform or bromoform. Okay. First thing you do is basically, we'll focus on chloroform. Take chloroform and you subject that to hydroxide. Turns out it can remove that proton. Okay? And again, let me just draw it out a little so it's a little easier to see. What will happen is that you can form your carbene because these two electrons just go on the chlorine. When that happens, you form your carbene and a chloride. Okay, now, before you say, what? Is this possible? And the answer is yes. Everything's possible. However, this is the reason that this is so important. First, for my chloroform, because this is so electronegative. Down here, okay. This is so electronegative. I have a positive proton. So when I do this, it's easy with chloroform for the hydroxide to remove that hydrogen. Okay, so this is more stable, and you can form enough of it that you can now move on to form your carbene. And this is the same that can happen with bromoform. Okay, do you form a lot of it in solution? The answer is no. However, here's the thing. When I do that, then when you form your carbene, there's less than an equilibrium going back. And that's how we draw it forward. So here, the first step that happens is, like we showed you previously, you form water and my ion here, our carbon ion. Second, my carbon ion here will disassociate, forms my carbene and my chloride. And the third, which is very fast, is my carbene will react with my alkene. Let me move this down. Okay, and it's because of this step I start using up my carbene. Therefore, with Le Chatelier, I know that I have to form more. So it's going to drive this reaction, this equilibrium forward, because I'm using up all my carbon ion. That means that this equilibrium is going to be driven forward. Okay, so that's my alpha elimination, carbene formation and synthesis. Okay, now let's talk about a few other things now that we're working with three-membered rings. Okay, so let's move on to epoxidation. So remember, an epoxide looks like that. Okay, so what about epoxidation? So what are the different ways we can make it? So the first way we can make it with an alkene is we make it with a peroxy acid. So two hydrogens, or oxygen, excuse me, there. What you form is you form your epoxide and your carboxylic acid. Okay, so it can be written this way. You can also see it as RCO3H. Okay, that's another way we write it. Okay, when we get to the specifics on it, I'll show you some of the, besides that, some of the major peroxides that we use, peroxy acids that we use. Okay, so you know what to look for as my reagent. Another way to do epoxidation is in two steps. The first step is to make your halohydrin. So, your halogen with water. Okay, so you might see bromine water or chlorine water. So that's step one. Okay, Notice we'll always number it if it's multiple steps over the arrow. The second step is you use something like hydroxide. You use a base. Okay? And this performs an SN2. Okay, so you do a backside attack. When you do that, you will form an epoxide. Okay? So, let's go through. Let me show you the first one. Let's talk about the reagents that we use in epoxidation. So the reagents that we use, they're peroxy acids. General formula looks like this. Essentially, you have an additional oxygen between your OH and your carbonyl group and your carboxylic acid. So the two most popular peroxy acids that we use is peroxy acetic acid and MCPBA. And what does MCPBA stand for? It stands for meta chloro peroxy benzoic acid. Okay, so let's do a few examples now to show you how epoxidation works. Suppose I take this alkene and I add in, let's say, MCPBA. Okay. So the product I get, I'm going to rotate this, is that you're going to have your methyl group in the back, the hydrogen in the front. This one, the methyl group in the front, the hydrogen in the back. And there is my epoxide. And the rest of the reaction, you'll just get a metachlorobenzoic acid. Okay? So, this is chiral, a hydrogen in the back. So, you have to say plus enantiomer. Okay? To make sure I know. Now, how does that work? Remember, if I draw in and I rotate out my methyl group in the front, hydrogen in the back, hydrogen in the front, methyl group in the back. Here's my double bond. My MCPBA can approach from the top, that forms this one, or if it approaches from the bottom, it'll form the enantiomer. Because remember, these are trigonal planar. So my reagent can attack from either side. Okay, so let's go through the mechanism. Alright, so if we go through the mechanism, I'm going to draw this not horizontally but vertically. Just hang on 1 second. Okay, so this is my peroxy acid. Okay, it's draw my alkene. Okay. So how does this work? This is a concerted reaction. So all the arrows I'm going to draw, the bonds that I form, and the bonds that I break will all occur at the same time. Okay? So my lone pair takes a hydrogen. These electrons form that bond to that carbon. These electrons go back to that oxygen. These electrons go here. And these electrons go right back up there. So what we form, actually I'm going to use blue. And then with the orange I'll show you the bonds that are formed. Okay. This one got broken, so this one stays. There's my oxygen. These lone pairs form a bond here. That bond forms a bond here. It's not pretty. I'll put it up in just a moment. Okay. So that bond forms there. I have a lone pair here. And then again, I form the lone pair there. This formed the double bond here. So basically, we've just, in a concerted fashion, go 1, 2, 3, 4, 5. So you're forming, when this rotates and forms a pseudo 5-member ring, because it's not a ring yet, when you form a 5-membered type of situation, configuration, then this sticks out. This is because of the electron withdrawing group here, and this is being taken here. This is delta positive. So basically, with this attack, now I form my carboxylic acid, and that's exactly what happens with a peroxide acid. Okay, and that's how you form your epoxide. So this is your mechanism. It's a concerted reaction. All happens at once. Okay. Now, let's talk about using halohydrins. So, if I take my alkene, okay, and let's say I react it with, let's do bromine water today. Then, we know in a transorientation, get a bromine here, get a hydroxide here, and you can get the enantiomer, okay? It's chiral, all right? So, when this happens, this is step 1. Now, with step 2, I'm going to add a base, okay? So my base takes off this hydrogen to form water, and so this does a backside attack in SN2, removes the bromine, and now look at that, bromide and water. Okay? So with each step, we'll revisit this mechanism again, and then we'll look at that mechanism. and then we'll do an example. Okay? All right, so step 1. Here's my alkene. Get my bromine, right? And what we do is add we do our electrophilic addition, kicks this out, and then my lone pair comes back. Okay. When we do that, what we form is my bromonium ion. Okay, so far so good. So, and normally, if I didn't have water present, this would come back, but don't forget, I have water present. So my water will act as a nucleophile, and it'll do a backside attack. Okay. What I get is my potent alcohol, which will lose my hydrogen to solvent or to the bromide, and then what I end up getting is my halohydrin. Okay, so that's step 1, my halohydrin. In this case, it's a bromohydrin. Right? So let's continue. Now, for step 2, we're going to add the base. So, I'm going to add base, and being a strong base, it will pull off the hydrogen. Okay, so what I form is a halo alkoxide. Okay, so think about it. This is a really good leaving group, and I'm perfectly oriented for a backside attack. I've got a base right here. So what happens is this attacks this carbon, and the bromide leaves. So what I end up with is my bromide. And when this comes as a backside attack, this carbon gets inverted. And now you have your epoxide. Okay. So what we'll do next is we'll do some examples, and then we'll talk about stereochemistry. Okay, let's do a couple examples for formation of epoxides, and then we'll move on to our next topic. And that is going to be epoxide opening. Let me just give you one more. Sorry, I was just thinking I should give you one more. Okay, so in this one, when we form our epoxide, okay, notice the relative orientation, okay, of my methyl groups. If they're trans here, they will be on opposite sides of this bond right here, okay? If that's the case, and don't forget, this is chiral, so this is plus an enantiomer. Okay, remember, MCPBA is metachloroperoxybenzoic acid. If we look at just a generalized form of a peroxy acid, when we draw this product, we'll get this epoxide. Again, the methyl groups are going to be on the same side across this bond. Because this is a meso compound, it's achiral. Okay, so this is the only product you're going to get. Now on this one, remember, we're going to go through and the first thing you're going to do is form, let me just go through this. Your halohydrin. This is from step 1. Okay. It goes in the back. So, let me just make sure. So, when I put in my chlorine here, I tap from the back. This goes here. This goes in the back. This hydrogen goes here. Okay. So far, so good. Now, when I do step 2, get my final product, I'm going to form this meso compound. Now the question is, if I rotate this, because it's an SN2, I actually can't get this epoxide. So be aware that you can maintain your stereochemistry even when you do the halohydrin. So with my halohydrin followed by my sodium hydroxide or my hydroxide base, you're going to form this compound. If you use peroxy acids, you're going to get this compound. So the stereochemistry of your product is going to depend on the stereochemistry of your reagent. And that's really important to know about epoxide formation. Now, let's go through and talk about, now that you know how to make it, let's talk about how you break it. So, what about epoxide opening? So it turns out, epoxides, okay, are sensitive to acid. Can they be sensitive to base? They actually are sensitive to base as well when it's concentrated, when you heat it up. So just be aware of that as well. But let's focus on the acid opening. If I take my epoxide, and I have, let's say, acid and water, then what you form is a diol, 2 alcohols, okay? You can do the same thing with acid and an alcohol. And what you get is an alcohol ether. Okay, so let's go through the mechanism with a reaction. So for the first one, we'll do two reactions. Let's do okay. So if we take this ether, so it's a methyl epoxide, okay, and I react it with acid as my catalyst and water, then what's going to happen is you get this. This opens up. I apologize for drawing today. Okay. All right, so far so good. So let's go through the mechanism to talk about why you would only get this product. Okay, so the first thing that's going to happen for your mechanism is you're going to protonate your oxygen. Okay, what you're going to get is basically your protonated epoxide. Now when you look at this, remember this could be like when we were looking at the transition states in my hydroboration, oxidation reaction. So there are two things that can happen, okay? When you look at it, this could start breaking. And you can share some of that positive charge here before basically all my electrons go here, and you'd have a positive charge there. Sorry, that's a methyl group here, my hydrogen here, my two hydrogens here. Okay, another possibility is this. Instead of this bond breaking, the other possibility is this bond on this side is breaking. And in that case, remember that's a positive charge. Now as my electrons are going in this direction, it becomes a delta positive, it's share here. If my electrons go in that direction, and that positive charge now gets shared between this oxygen and that carbon. And when you look at it, the question that you need to ask is this. Which is the more stable carbocation? This one, this carbon, has a carbon and a carbon attached to it. Okay. This one just has one carbon. This is primary, that's secondary. So this is the more stable. This is secondary. This is primary. So this one is a more stable carbocation, which means when my water comes in to attack, okay, is going to go to the more substituted carbon and leave the less substituted carbon alone. Okay, so that's what would happen. And then, just dry here, you would get, that gets pushed up because it is a backside attack. This is an SN2. Make this a little more obvious. It's pushed up, it's inverted. I don't like my drawing here. There. That looks better. That's inverted. Then I have my hydrogens here, hydrogen there. And now I have my leaving group, okay, which is still attached, okay. So now I'm just going to lose my H plus to my solvent. And I have my diol. Okay, so because I started off with something that was chiral, my product, because of the way this reaction works, is going to be chiral. And it is regioselective. So if you think of this being my good leaving group, I am doing basically an SN2 backside attack, but because with my acid, I'm forming a better leaving group, and it's going to have that charge on the more, to form the more stable carbocation, it will only give you this isomer and not that one. Or there is a regioselectivity, so definitely this one is preferred. Okay, so let's do a series. Okay, so suppose we do okay, so if you think about it, this is a two-step synthesis. Okay, so it's not like a, yeah, all these are going to be in the same reaction mixture. You're going to do this reaction first, and then do that reaction. When you do, you're going to form an epoxide from the first one. It's going to be above or below. And then, when I open it with the acid, one side gives me a diol. I have an alcohol here and an alcohol there. Okay. Notice when I do this type of opening, I have what we call a trans diol. Okay. They're on opposite sides. And this is chiral. You're going to get the enantiomer. All right. Now, what about an alcohol? If we do the same thing, 1 MCPBA, and since we know 2, let's just do methanol, something small. Okay. What happens is, where does the methanol go? It will go On the side that's the more substituted carbon, because that's where my more stable carbocation is. So you're going to end up forming, this will be my ether, and this part will be my alcohol. And again, you get your enantiomer. Okay, so if you're unsure where this one will go, just work out your mechanism, make your epoxide, protonate it, and look where the more stable carbocation is going to be. Okay, so you're forming your groups in the trans orientation. What happens if I want a syn, especially for the diol? What happens if I want a syn diol? So if we want a syn diol, okay, we're going to do basically either permanganate or osmium tetroxide. So we have here my alkene, and when you use potassium permanganate, make sure it's on the cold side, preferably neutral. Okay, and the reason you want it that way, because if you continue in more harsher conditions, okay, for harsher conditions, cold, basic, you have harsher conditions, what's going to happen is it'll continue, and we'll talk about cleavage of these double bonds. So you're going to form so you're going to form a diol, but in this case, it's in the syn addition. Okay, or besides potassium permanganate, which is called osmium tetroxide. Okay. Okay, so making a diol in the syn orientation, you're going to use osmium tetroxide, or you can use potassium permanganate on the cold side under basic conditions.